Okay, so the last topic of the chapter handout has to do with heat and specific heat. So let's talk about heat for a second. Heat is different than temperature, okay? So heat has to do with the total energy of something, and heat flows from a warmer object to a cooler object. You're going to want to write that down. And there is a unit of heat known as the calorie. It's a lowercase CAL, okay? So, calorie, which is this, is a lowercase CAL. That's really important, okay, because a capital CAL is something else. This is the amount of heat necessary to raise a gram of water by 1 degree Celsius. You need to know the definition and know that the abbreviation for this definition of a calorie is a lowercase CAL. Okay, another unit of heat is the joule. And the joule is a capital J. Okay, so this is already typed up for you in your handout, which you got before you started watching this video. Okay, this is the international system. This is their unit for heat. Okay, now I gave you in the chapter handout a few unit equations that you may use to perform some sort of conversion of heat units, okay? You don't have to memorize them. You will always be given them, okay? Now, the one that is sort of logical, which you can kind of make sense of without even knowing it, is this one, okay? 1 kilojoule equals 10 to the third joules. Remember, kilo is 10 to the third. So that's why the 10 to the third is over there on the other side with the one-letter unit, joule. And I put the number 1 next to the prefix, which is kilo. Okay? So let's take a look at student exercise number 29. Burning a liter of natural gas produces 9.46 kilocalories of heat energy. Express the energy in kilojoules. So this is what I'm asking you to do right here, okay? And I gave you the unit equation after the problem in parentheses. Can you guys please stop talking while I'm filming the videos? Thanks. So we're going to put 9.46 kilocalories in the upper left-hand corner like this. And then we're going to put kilocalories on the diagonal. And we're going to put kilojoules up on top. And it says that 1 kilocalorie is 4.184 kilojoules, like this. So we're going to multiply this across. So it's 9.46 times 4.184. You want 3 sig figs in your answer. I got 39.58. We're going to round it up. It's going to be 39.6 kilojoules. So here you go. Okay? Now, student exercise 30 says, if an aerosol can feels cold after releasing the spray, is heat flowing from the can or from your hand? When something feels hot, like if you're heating up water in a pan, okay, and the pan feels hot, the heat is flowing from the pan to your hand because your hand is cooler, and I told you at the beginning of the video that heat flows from a warmer object to a cooler object. So if you're feeling an aerosol can and it's cold, then heat must be flowing from your hand, which is warmer, to the aerosol can, which is cooler. Okay, let's talk about specific heat. Specific heat is the amount of heat required to raise the temperature of a gram of something by 1 degree Celsius. You need to know the definition, and you need to know that in general metals have low specific heats. That means they cannot absorb a tremendous amount of heat energy before their temperature increases. And water has a really high specific heat in comparison, and you can see this in the data table that I gave you in the chapter handout. It's table 3.4 right here, okay? Water has a specific heat of 4.18 joules per grams times degrees Celsius. That's much higher than most metals, which are around like 0.1, 0.2, 0.4. Okay, so that means that water has the ability to absorb a tremendous amount of heat before its temperature increases. So this is the reason why coastal towns stay cool, because they're surrounded by water. Water is absorbing all that additional heat from the summertime, and it is really nice during the day. Okay, now the units for specific heat, also known as heat capacity, tend to be a fraction unit, like joules divided by grams times degrees Celsius, and this is typed up for you in your chapter handout, or you'll see them as calories divided by grams times degrees Celsius. So these are the way that the units tend to look for specific heat. Okay, so when you see a number with a crazy fraction unit after it, it's probably specific heat. Okay, now, student exercise 31. If you wanted to heat a metal plate to as high a temperature as possible for a given energy input, you would make the plate out of copper, iron, or aluminum. So let's see, copper, iron, and aluminum. Here are the symbols for copper, iron, and aluminum, okay, which you've probably become familiar with in middle school. Copper has a specific heat of 0.385. I'm going to exclude, no, I'll write in the units for you. Okay. Iron has 0.449 for its heat capacity. And then aluminum is 0.903 joules per grams times degrees Celsius. You want to pick the metal that has the lowest specific heat, because that metal cannot absorb a lot of heat energy before its temperature starts to increase rapidly. Okay, so I would pick copper because I don't have to put a lot of heat energy in to get its temperature to increase. This is one of the reasons why we have copper on the bottom of pans that we use to cook with, because it helps us get that pan to a higher temperature quicker. We don't have to use as much energy, and the pan will get really, really hot. Okay, now there are some other calculations that you have to do with heat, and let me show you what the equation is. Okay, this equation you will be given on a test, and on the final you never have to memorize it, but you have to know what the different variables stand for. Q stands for heat. Heat typically has units of joules or calories. Okay. M stands for mass. Mass has units of grams, which is a little tiny g. C stands for specific heat or heat capacity. It has a fraction unit, which I showed you earlier, like joules per grams times degrees Celsius, or calories divided by grams times degrees Celsius, which is this. The change in temperature is, which is what this triangle stands for. The triangle stands for change. Sometimes they call it, sometimes they call it delta T. Okay, this is going to be the final temperature minus the initial temperature. So I'm just going to write TF minus TI, and this is in degrees Celsius. That is the one place where students go wrong. They forget that it's the final temperature minus the initial temperature. So when you are reading these problems, you have got to make sure that you are subtracting the temperatures correctly. Okay? Sometimes it may be negative change in temperature, and sometimes it'll be positive, and that's totally fine. Okay, now, that's the equation that you use if you're solving for heat, which is Q. If you are solving for mass, the reason I'm telling you this is because sometimes students have a really hard time rearranging equations to solve for a variable. And that's something that you were supposed to be doing in Algebra 1 in middle school and then freshman year. And at this point, you should be able to rearrange it. But if you have a hard time, then just memorize the different forms of this equation. So if you're solving for mass, this is what you're going to do. It's going to be the heat divided by the heat capacity times the change in temperature. Okay? If I ask you to solve for heat capacity, which is C, it's going to be Q divided by mass times the change in temperature. So it would look like this. If I ask you to solve for the change in temperature, it's going to be delta T equals Q divided by M times C. So it would look like this. And then there is one more, which is the final temperature. Okay? So if you're solving for the final temperature, which in my opinion is the hardest, you're going to use this equation. Okay? So it's going to be heat divided by mass times specific heat, and then you're going to add the initial temperature to it. Okay? This is the hardest one. All right, so let's take a look at a couple examples. Student exercise 32. You've got gallium metal, and you're holding it in your hand. It melts from body heat. You've got 2.5 grams of it. The temperature is raising from 25 to 29.9 degrees Celsius. The specific heat is 0.372. So we want to know what the heat is, how much heat is going to take to melt it. So we're going to put 2.5 grams in for mass, 0.372 joules per grams times degrees Celsius in for C, and then 29.9 minus 25 degrees Celsius in for the change in temperature. So it's going to look something like this. Let me give you some pointers. Do the subtraction step where you're lining up the decimals, 29.9 minus 25.0. Do it like this. This is the one place where you're going to have a sig fig change, because most of the time students forget to do this. So you're going to get 4.9 here. That's 4.9 degrees Celsius, and that's what that is. Okay? That's 2 sig figs times 2.5 times 0.372. I got 4.557. I'm going to make it 4.6. Grams are going to cancel. Degrees Celsius are going to cancel. I'm going to be left with joules. So it's going to be 4.6 joules, which is the unit for heat energy, and now we're good. Okay. Student exercise 33. A chemistry student finds a shiny rock that she suspects is gold. She weighs the rock on a balance, and the mass is 14.3 grams. She then finds that the temperature rises from 25 to 52, and it absorbs 174 joules of heat. What's the heat capacity of the rock? Okay, so heat capacity, which is C, is going to be Q divided by mass times the change in temperature. So it's going to look something like this. So we're going to put 174 joules up on top. The mass is 14.3 grams. It goes on the bottom. You're going to multiply it by 52 minus 25 degrees Celsius. Okay? So you're going to do something like this. So it's going to be 174 divided by 14.3 times, parenthesis, 52 minus 25. Probably going to have a sig fig change there in the 52 minus 25, which is 2 sig figs. You want it to be 0.45 joules divided by grams times degrees Celsius for your unit. And that's it. Now, the specific heat worksheet, which corresponds to this lesson, looks like this. Okay? You have to show all of your work. Watch your sig figs, do that subtraction step where you line up the decimals and draw the line. Make sure you have the right units.